Hello, good people. Here we are in the next video. We're going to transition now to working with use substitution in definite integrals. But before we do that, let's kind of recap what we know about definite integrals. We have three important components in definite integrals. The first one is the limits of integration. The limits of integration, if you recall, tell me where to begin and where to end my area finding, right? My shading under the curve, where to begin and where to end. The second part that's important is this part, which we call the integrand. The integrand tells me the function that I'm going to use to find the definite integral. And then the last part that's important is this. We call this the differential, also known as the dx. The dx tells me, in a very kind of basic sense, it tells me what variable I'm using to take the integral. But what needs to be true is that these values that are up here need to be in terms of x, just like this function needs to be in terms of x. So all three things need to have the same variable. And when we do use substitution and we change the variable structure, then we also need to make sure that the limits of integration values change as well. So here's the new twist. There's good things and bad things about it, but let's keep in mind what we're talking about. If we use substitution with a definite integral, in other words, I have a starting point and an ending point, I see numbers on my integral symbol. If I'm using use substitution, then I have to also remember to change the limits of integration. Let me use the color that I used to write those words, because limits of integration. It's a pain because I'm going to have to change these numbers. However, the nice thing is I'm not going to have to go back into the world of x's. Once I change everything, then I can continue in the world of u variables and not have to go back to the world of x variables. So and then that's what Brian is reminding us here. If with definite integrals, we do not want to convert back to x after integrating. Can we? We can. However, it's going to take time, and time is not something that you have on your side, right? So we're going to do example 7 in this video to kind of get the idea of how to do, actually we might do 7 and 8 in this video to get the idea of how to do the whole use substitution process, but now with definite integrals, how to take into account these limits of integration. Okay, so let's do step 1. What is my u equation? My u equation, I think, could be x squared plus 4. I say that because that's the only inside function that I notice. Knowing that, can I find du? Well, du is the derivative of x squared plus 2x, and that would be 2x dx. I'm getting ready to do my substitution. Do I have enough to change my dx for du? I do, because if you look, I have 2x dx. I need 2x dx, so that's going to be a clean switch. And then x squared plus 4, well, that's going to be replaced by u. And so I'm going to start my substitution and say this is really u to the third du. However, I should not put these numbers here. Why? Because now I'm not in the world of x values anymore, and these are x values. And so what we can do is convert them into u values. And so one way we can do that is take your u equation and let's plug in. So u is going to equal, if I plug in 1 into my u equation, my u value on top is going to be 5. And if I take my u equation and substitute 0, my u value on the bottom is going to be 4. And that's it. What have we done? We have changed not only the expression, the integrand, and the differential in terms of u, but I've also changed my limits of integration to be u values, not x values. And this is important. Putting 0 and 1 here can cost you points. So please don't do that. If you're going to switch, if it's a definite integral, this is only if you have limits of integration. If it's a definite integral, when you switch to a u expression integral, then you got to do everything, change everything. Okay, now we're ready to take the antiderivative. The antiderivative of u to the third is u to the fourth divided by 4, but we need to evaluate this at 4 and 5, right? Remember, we draw this little line to remind us we're not done. We still need to plug in the values, because the fundamental theorem of calculus says if I substitute the top limit of integration, I don't know why I put a 2 there, into my antiderivative, and the bottom limit of integration into my antiderivative, and subtract them in that order, top value minus bottom value, then I'm going to get the exact answer. I'm going to get the exact definite integral that I need. Let's see. Can I simplify this at all? I don't think so. 5 to the fourth. Well, 5 to the fourth is 5 squared times 5 squared. 5 squared is 25, and 25 times 25 is 625 divided by 4, minus this is 16 divided by 4. And if I subtract, I believe that's 619 divided by 4. Is that right? No, 609. My bad. 609 divided by 4. This is my definite integral answer. This is the answer to this definite integral. I don't need to go back to the world of x's. I'm done, because once I switched everything into the world of u's, whatever answer I got there, because these are equivalent, then that's my answer. This is number 7. Easy peasy, mac and cheesy. So think about what we did. How is it related to what we did in the other videos? We had to identify the u. We had to find the du. We had to make sure we had enough to make the exchanges that we needed. But this time, the new part is I have my limits of integration. I have to convert those as well. But the good news is once I take the antiderivative, I can plug these numbers, these new limits of integration, and whatever I get as my answer, that is the solution. That is the definite integral value. Let's try it again. We'll do example 8 and then we'll pause. All right, can you identify the u? I'm going to say u is 2x. What would be du? Du would be 2dx. Do I have 2dx? I don't. So I'm going to multiply a 2 here, but I can't just willy-nilly introduce a 2 without balancing it out with a 1/2 on the outside. I do that so that everything stays equivalent. But I needed this in order to make this exchange. And so now I'm going to say this equals, or maybe I'll do that pink arrow that I did before, the integral of sine of u, and the 2dx I can replace with du. Don't forget, I still have this 1/2 in the front. And then let me change these u values. So u is 2 times my x value. The top x value is pi over 2. So that's going to produce just pi. U is equal to 2 times pi over 6. That's going to reduce down to pi over 3. And that's my bottom limit of integration. Great. So once I find the antiderivative, I can just plug in these numbers and I'm done. But I need to find the antiderivative. What's the antiderivative of sine u? That would be negative cosine u. And don't forget the 1/2 is still there. So negative 1/2 cosine u, but we're going to evaluate that at pi and at pi over 3. Think about how we got to this point by taking the antiderivative. And now the fundamental theorem says if you substitute the top limit and evaluate it into the antiderivative and take the bottom, I got to be careful. The fundamental theorem says to subtract them, but this also has a negative 1/2, so I got to be careful here. Cosine of pi over 3. Now can I do this? Well, cosine of pi, what is cosine of pi? What is the x-coordinate on the unit circle at pi? I believe that'd be negative 1. So negative 1 times negative 1/2, that's positive 1/2. Here, these two become plus 1/2, and then cosine of pi over 3. Cosine of pi over 3 is 1/2. So really, I have 1/2 plus 1/4. So that would be 3/4, and that's my answer. The moral of the story is use substitution can help us with complicated looking integrals that we have to either anti-differentiate or solve by hand by making my integrand look simpler and to a point where I can actually do one of my antiderivative rules that we have been looking at as a reverse of the regular derivative rules. We'll come back with the next video. We'll do some more of this definite integral practice. But again, the whole idea is we're trying to make something complicated look less complicated. And look at number 9. We're going to make that look less complicated so that we can take the antiderivative and use the fundamental theorem of calculus in order to find the exact definite integral value.